I'm going to talk also just about a specific problem and not a very overview thing. I'm going to be talking about approximating k-center in graph. And so I think the key point I'm going to try to make with this talk is how to use the gaps from one kind of problem for a different kind of approximation, which we'll see later in the lower bound. We're going to get this lower bound from set cover where the gap feels very different in the lower bound we're proving versus the gap that we get in set cover. So first I'm going to introduce this problem and kind of motivate the lower bound that I'm going to be talking about for most of this talk. So I'm going to introduce the k-center problem and show what was known before this work, which was basically that a 2 approximation is easy. We can get it in linear time. But anything better than a 2 approximation takes n to the k time. So then to kind of avoid this problem and have something to talk about, we're going to introduce small additive errors to this problem and show that in this case, we can actually, we're no longer stuck in this 2 is easy, better than 2 is hard, and we're going to beat the 2 approximation. I'll just kind of mention the algorithms that can beat this lower bound. And then for the rest of the time, hopefully I will have motivated why this is a problem that we care about, and I will talk about this lower bound from gap set cover. So the problem I'm going to be talking about is k-center in graphs, which we want to find k points in the graph that minimize the maximum distance of a vertex in the graph to this set of centers. And what we're going to try to approximate is the radius here. So that will be this maximum distance. So it'll be this maximum distance of a point to this set of centers. So here the approximation is not going to be in terms of k. It's going to be in terms of this radius r, which when we think about the gap problems we've seen mostly in this workshop, usually they would correspond to a gap in k, like approximating the number of points we'd need in order to cover the graph. But here, what we're approximating is, in fact, this distance. And I'm going to say k radius, k-center radius, all of them are going to mean the same thing. And I'm going to say like a bunch of points cover the graph if within this distance r, if everything in the graph is within distance r of this set of points. So as just an example for a k-center, say we have this graph and we want to find 3 points or a 3 center, then if we take these 3 points, we see everything else in the graph is within distance 2 of them. And this comes into play with clustering, because now we can assign every point to its closest center and get some way of clustering the graph. So this is usually where this problem comes up. OK, so I mentioned that a 2 approximation for this problem was known. So actually, a greedy algorithm gets us a 2 approximation. So say that we know what r was. We can get rid of this assumption, but just assume that we know what this optimal r is. We can just greedily choose centers. So we start with just an arbitrary vertex. So this vertex will be within distance r of one of the true centers. So anything that was close to that original center will be within distance 2r of this arbitrary vertex. So we assign to its cluster all the vertices within distance 2r, and now we've covered at least one of the original clusters. So we can just repeat this. Now we pick another arbitrary node and assign to its cluster everything that's within distance 2r. So after at most k steps, we will have covered the entire graph within distance 2r of these nodes that we picked for our centers. So we had to repeat this k times, and each time we did just like a linear search. So we get this runtime that's basically linear. We have a k factor. And we can even get rid of this k factor if we allow for a 2 plus epsilon approximation. But in not just polynomial, but linear time, we can get a 2 approximation to this problem. And on the other hand, this is the entire slide. I can show you a lower bound that shows you a better than a 2 approximation is hard. So we start with k dominating set, which has come up also in this workshop before. So we know that under strong ETH, solving k dominating set takes n to the k time. And then we notice that dominating set is kind of a form of k-center. It's kind of the optimal form. A k-dominating set is a k-center with radius 1. So if there exists a k-dominating set, the optimal radius is 1 in an unweighted graph, and otherwise it's at least 2. So anything better than a 2 approximation solves dominating set needs n to the k time. OK, so if this was the problem, a 2 is easy, better than 2 is hard, what am I going to talk about for the rest of the time? So we noticed that this 2 approximation is hard only really in this dominating set case. It's only really hard when the optimal is 1. And that's not usually the case that we care about for k-center. So to beat this lower bound, we're going to introduce additive errors, which I think everyone knows, but I'll put up the definition. So we're going to call an approximation like a multiplicative alpha additive beta approximation if the value that it outputs is between the true value and this alpha r plus beta, where again the thing we're approximating is this radius. So in weighted graphs, even when we allow this like additive error, this is still hard. The K-center is still hard to approximate. And in the 80s, Hochbaum and Schmois showed that under strong ETH, any kind of 2 minus epsilon approximation, even when you allow additive error, needs n to the k time to solve. But the key thing is this reduction relies on these edges scaling up with beta. So what if we don't want to do that? What if we don't let the edge weights scale up with our error? So can we achieve a 2 minus epsilon approximation with a small additive error faster than n to the k time in, say, unweighted graphs, where we don't allow the weights to scale at all? So the answer is yes, and I won't go too much into it. I'll just kind of give a little motivation on where this problem is different and why now that we allow additive errors, we can do a little bit more. So a first result that I'll give like a little bit of information how we do it is we can get a 3/2 approximation in this runtime that's like slightly better than n to the k. So it beats the lower bound, but it's by a little bit. Still, it's n to the k minus a little bit. So we notice that if we're not in this dominating set case, so if the optimal value is not 1, this is purely better than a 2 approximation. So the idea of this algorithm is, this is a somewhat standard idea in these distance approximation algorithms in graphs. We're going to, given this r, this optimal r, we're going to try to find k points that cover the graph with a radius r plus r over 2. And the only part that's an additive approximation comes from this ceiling of r over 2. So if r is even, it doesn't even have an additive approximation. So our algorithm will sample a hitting set, will run APSP, compute all the distances, sample a hitting set, and then it takes the furthest point from the hitting set and some neighborhood of this point. And we're going to claim that either our hitting set has a good approximate k-center, so it has k points that cover the graph within this radius that we want, this distance r plus r over 2, or some point in our set W will be close to one of the centers. And I won't prove this claim, but it's similar to, it follows from similar logic to a lot of like distance diameter approximation algorithms. And this just gives us these two cases where the first one is that k, this hitting set S itself has a good approximate center. So we can just iterate over all the k tuples in S to find it. And the second case is that there's some point in W that's close to a true center, which means that that point will cover that cluster of that original center with radius r plus r over 2. So if we iterate over all the k tuples that use a point in W and just k minus 1 points in the rest of the graph, we'll find a good approximate center. So if you look at what the runtime of this, it actually doesn't come out to better than n to the k. Like we get some n to the k plus delta from the size of the hitting set, but we can beat this with fast matrix multiplication, where we can, instead of computing brute force these k tuples, we can use a matrix to compute it. Well, and again, since the point of this talk is more the lower bound, I'll just tell you that if we balance out these runtimes, we get that for different values of k, it balances out a little differently with the matrix multiplication. But in all cases, this is faster than n to the k. We get some faster algorithm than some algorithm that barely beats n to the k, but the approximation is 3/2 and not 2. And we can kind of extend this idea all the way down to a 2 minus 1 over 2k minus 1 approximation, where the runtime is n to the k over 2, basically, and not n to the k. And these algorithms can also be sped up with matrix multiplication. But yeah, the key is that that this lower bound is no longer true. This lower bound of n to the k is no longer true when we're allowing this additive error. So hopefully I've motivated this problem a little bit, and now we're going to talk about about the lower bounds, because this is a workshop on lower bounds. Okay, so the lower bound we saw before showed that we can't get a purely multiplicative better than 2 approximation. But now we're in the setting where we're allowing these small errors. So the question is, can we achieve a 2 minus epsilon approximation? If we allow an additive error, can we do that in linear time? So the answer to that is no. And under ETH, we actually can't get any algorithm that runs in f of k n to the little of k time that will achieve a 2 minus epsilon approximation when we allow even when we allow this error. Okay, so in general, what is the approach to a lower bound when we care about additive errors? Right, when we want a general lower bound for a graph problem, we take some problem that, like some hardness hypothesis, takes tn time to answer, and then we construct a graph where we have, if the answer is no to the problem, then this parameter that we want to approximate is less than some value q. And if the answer to the question is yes, then the value is more than alpha times q, right? So better than an alpha approximation distinguishes these cases, solves that hardness, that problem where we have some hypothesis on how long it takes. But this is where, like, but what do we want to do differently when we need to allow for an additive error as well? We want to be able to scale this graph up to account for the additive error. So instead of having this dichotomy between less than q and more than alpha q, we want to be able to scale this with some for every integer L, say. So we want to construct a graph for every L where if the answer to the question is no, then this parameter we want to approximate, the radius, is less than LQ, and if it's yes, then the radius is more than alpha LQ. And therefore, for every additive error, we can just take a big enough L so that this approximation will tell these two cases apart. Okay, so in the lower bound that we had before, this dominating set lower bound, if we want to be able to scale this gap up, this q to alpha q, want to scale it up with every L, that's where those edge weights would come in. We'd need the weight of the edges to scale up with L, which is what we don't want to do. So this k-dominating set doesn't work anymore when we want to allow additive errors. Okay, so what is going to work, we're going to show a reduction from set cover. So we're going to start with set cover and then talk about gap set cover, as I mentioned. So set cover instance, which we've heard about yesterday, we have a bipartite graph with parts A and B where we want to find a subset of A that is adjacent to all the vertices in B. So some subset in A covers all of B. And under strong ETH, even deciding this K set cover, so even deciding if there's a size K solution to set cover takes n to the K time. And this is true even when B is very small, when B is logarithmic in n. Okay, so this will be our hardness hypothesis, and now we're going to construct this graph gadget to represent set cover. So this will be our sets A and B from the set cover problem. And now we're going to replace the edges between A and B with paths of length L, where L is that thing that we want to be able to scale. So the size of our graph just scales with L. So we're going to replace the paths, the edges with paths of length L. And we're just going to add, for every vertex in B, we'll add a tail of length L. And we're just going to add another vertex C and connect it to A with paths of length L. So all these are length L paths. So this will be our gadget, our set cover gadget that we'll see a lot in this construction. So first, we'll see that if there exists a size K solution to our set cover problem, then the K-center radius of this graph is going to be less than 2L. So why is that? If we have a size K solution, so we have K vertices in A that are adjacent to all of B, we can just click the wrong button. If we have K vertices that are adjacent to all of B, we can just take those to be our centers in A. And now everything in anything up here will be within, or in this half of the graph, will be within distance L of a vertex in B. And that vertex in B had a neighbor in this set cover instance. So within distance 2L, we can get back to one of our centers that we picked. And anything in this half, we can just go within distance 2L and cover all of it from any arbitrary point in A. So if there exists a size K solution to our set cover, we can pick K centers that cover the graph in distance 2L. And on the other hand, if there doesn't exist a size K solution to our set cover, we'll say that the K center radius is at least 3L. So we can show this in the contrapositive. If the K center radius was strictly less than 3L, then we have K points in the graph that cover everything in distance less than 3L. So for each one of these points in our centers, we'll take the closest point in A. So if it's anything that's originally in A or in one of these paths, then there's a unique choice of which point in A to take. If it's anything up here, we look at the B that it came from, and we pick an arbitrary neighbor. And if it's anything here, if it's this vertex C, we pick something arbitrary in A. So if we have this K center that had radius strictly less than 3L, then we claim that these K points that we projected it onto A are going to be a solution to set cover. And why is that? If we look at a point in B, we want to show that it has a neighbor in this set cover that we've constructed. So we look at the end of its tail. So now it had a point in that set, in one of those K centers within distance 3L of it. So that can't be this point C. It has to be something else in the graph. We can just basically show that that point in A that we projected it to will have to be a neighbor of the point in B that this tail originated from. So K-center solution with radius strictly less than L corresponds to a solution to set cover of size K. OK, so far I've just used set cover, and I've given a construction that's it's like a very standard, or similar to standard techniques in like graph distance, lower bounds. And we've shown that better than a 3/2 approximation, even when we allow for additive error, because we can scale up this L, that a 3/2 approximation, better than 3/2 approximation, needs m to the k time. OK, but we were talking about a 2 approximation. So we want to take this lower bound a little further. OK, any questions so far about this first step?
Where the restriction you have to feel constant, like the additive error constant in this technique?
Sorry, what?
Like why this technique can only probe additive error up to constant?
So the additive error is up to this, the additive error depends on this L. So we want the graph to still be size n, so we want L to be constant. L can be, if L is logarithmic, then the graph size is like O tilde of m. But yeah, it comes into play just with the size of this construction. OK, so now if we want to extend this lower bound, now we're going to introduce gap set, which Karthik and two names I didn't practice showed is just as hard under strong ETH. So not only does it take n to the k time to solve set cover, it also takes n to the k time to distinguish between a size k solution and a size, and if there's no solution of size c times k. This is where this is the gap. And we're only going to be using constant c, which is true up to logarithmic c. So this is the gap set cover problem that we've heard about yesterday. So now assuming this stronger version, we're going to try to construct a 3 versus 5 lower bound. So we take this as basically the same construction that we had before, but now instead of paths of length L and L, we have 2L over in the paths between A and B and A and C. These tails are still length L. And now now in this graph, we say that if there exists a size k solution to the set cover, this will correspond to a k plus 1 centers with radius 3L. So instead of k centers we had before, we're going to have k plus 1 centers. We're going to take that size k solution and pick the k vertices in A that correspond to it, but we're also going to add this vertex C into the center. So we have k plus 1 vertices. And we need this extra vertex C. We'll see we need it to cover some part of the paths here. So in the same way we had before, anything that's within distance L of this set B will be within distance 3L of our vertex of one of our centers in A. But then to cover the rest of the graph, so anything that's within distance L of this set A and these paths, or this bottom half, we're going to use our extra vertex C in our center. So this blue path will cover anything in this bottom half of our graph. So yeah, so now if in the yes instance there is a size k solution, the k plus 1 center will be, the k plus 1 radius will be less than 3L. And in the same way we showed before, if the k plus 1 center, so if the k plus 1 center radius is less than 5L, then we can project those centers back onto our set A, and we get a solution to set cover. So since now to match this, we're starting with k plus 1 centers, we get a size k plus 1 solution to set cover. So here's where we see where the gap is somewhat different. Like the gap that we're using for set cover will be between a size k solution versus a size k plus 1 solution to set cover. And it's not this 3 versus 5 that we get for the distance approximation. So here we see that so under gap set cover, any 5/3 approximation, anything better than a 5/3 approximation, when we're allowing for additive error, needs this m to the k minus 1 time, because the problem we had was k plus 1 center, not k center. OK, is this next step clear? OK, so let's take this even further. Let's try to do the next step. Now, instead of 3 versus 5, we want to do 5 versus 9. So we can try to take the same construction that we had before, where instead of L, 2L, 2L, we take now 4L and 4L. We would like to get a similar thing, where if there exists a size k solution to our set cover, then we take those k, that solution here plus this vertex c and cover the graph within radius 5L. And otherwise, we get that the radius is at least 9L. But the problem is that if we take these points, if we just take k points here and 1 point here, we're not going to cover the center of these paths. So like we saw before, anything that's within distance L of this set B will be covered by one of this set cover instance A, like either like this. And anything that's within distance L of A will be close enough to this vertex C. So we've got this and this covered, but this middle 2L of the paths is no longer covered by these k plus 1 centers. So the solution is we're going to add another instance of set cover. We're going to add more centers to this problem. So we'll take this and we'll split our paths in half, and we'll add another copy of our set cover gadget. So this set cover gadget will have paths of length 2L, 2L, and 2L. And now for every vertex B, we'll look at the matching vertex B here, and we'll add a path of length 2L to all these edges that come out of it. And now we'll see that if there exists a size k solution to our set cover problem, then we can take those that solution here, the k vertices here, the k vertices here, plus these 2 copies of C, and these are going to cover everything within distance 5L. So now, to get to the middle of these edges, we'll take the corresponding center in A, and with like 2L, 2L plus L in either direction, we can cover these parts of the path. And we can show that everything else is covered by these centers. So this is like the condensed version. This is what it would look like kind of drawn out, this construction, where we have for every B, we have its copy, and we add these edges onto the middle of these paths between B and any of its neighbors in A. So in this graph, if there exists a size k solution to the set cover problem, we now have 2k plus 2 centers, so k here, and these 2 vertices that cover the graph with distance 5L. But if the k center, 2k plus 2 center radius is strictly less than 9L, then we can do the same argument where we project these centers onto the set A, and the vertices that we get, we can show are a set cover, our solution to the set cover. So now we're using a slightly bigger gap where in our yes case is, or one of our cases is a size k solution, the other case is a size 2k plus 2 solution. So here under gap set, or under strong ETH, we see that a 9/5 approximation takes m to the k over 2 minus 1 time. So now this is an idea that we can kind of iterate. So if we want to get, so for any general t, we can create this construction where we put 2t length paths here, 2t length paths here, plus this tail length L, everything times L. And then we add these extra centers to kind of cover, to be able to cover all these the points on the paths. So for every t, we're going to end up with this so at some point these constructions that we add to cover them will be long enough that they will themselves need another construction to cover. But for every t, we'll get some construction with some number of these copies of set covers, of this set cover gadget. So this will be our function f of t. And we'll get this construction where if our set cover instance has a size k solution, then we can cover the graph within distance 2t plus 1 times L using k plus 1 times f of t centers. So like k centers in each one of these copies of A plus all these vertices, extra vertices C. And on the other hand, if the ft k plus 1 center radius is less than 4t plus 1 L, then we can find the solution of this size for the set cover instance. So our gap here that we're using for set cover is just basically this k versus f of t times k plus 1. So it scales with this function of t. And that gives us our general lower bound. That we have this function f, which for these small values of t, so the examples we showed for t, 1, 2, 3, 4, it's just actually t. But for larger values of t, we can bound it by t squared, so it doesn't grow too much with t. So we have this function f that tells us that distinguishing between a 2t plus 1 radius and 4t plus 1 radius takes n to the k over f of t time. So this gives us this lower bound under strong ETH that anything better than a 2 minus 1 over 2t plus 1 approximation, even when we allow for additive error, needs this runtime that's bounded by k over f of t. So at most, at worst, it's k over t squared minus 1. So and in general, like we can't get a better than 2 approximation multiplicative, even when we allow this additive error, and without having a k in the exponent of the runtime here. We can't have this be anything, anything just a pure polynomial in n. And under ETH, this is still hard. So I think we heard about set cover under hardness under ETH. So the same construction, if we use the ETH lower bound instead of strong ETH, tells us that set cover, there's no f of k and to the little o of k time algorithm that can solve gap set cover. So our same construction will tell us that under ETH, we can't get a better than 2 multiplicative approximation, even when we allow additive error in a runtime of like f of k and to the little o of k. And yeah, that's what I wanted to talk about here. I think the key takeaway is not the problem itself, just this use of a gap in one sense for set cover to prove a lower bound for an approximation that's talking about distances and not number of points. And a lot of the problems that we use for lower bounds in distance approximations have their gap version. So it's, I don't know, this seems to be an untapped field where we could get more lower bounds. Yeah, thanks for your attention.
Questions?
Yeah.
Do you have any other sort of natural-ish problems that you think this could be applicable to?
So I don't know. It seems approximating diameter is a problem that has a big gap between the upper and lower bounds, and those are all based on different like KOV lower bounds, and those seem to. It seems like there should be a better way to do it if we used gap OV there instead of OV. I don't know how to do it, but that seems like a natural problem where the lower bounds might be improved using a gap version of the lower, yeah.
Maybe diameter-based clustering.
Yeah.
Any more questions? Okay. Not, let's thank Yael again.